Welcome back to the series. Most explanations of IAM fundamentals, users, groups, roles, and policies start in the wrong place. We're starting from the problem it solves. By the end of this video, you'll know exactly when to create an IAM user, when to use a role instead, and how Amazon Web Services decides whether each request succeeds or fails. Most engineers default to creating users with access keys for EC2, and that single habit causes a huge share of Amazon Web Services breaches. We're going to fix that habit today. In Episode 7, we drew the line between security of the cloud and security in the cloud. Amazon Web Services handles the physical infrastructure, and your half includes data, configuration, and identity. We also walked through the Capital One breach, where an attacker reached the EC2 instance metadata service and stole credentials belonging to an IAM role. Those credentials came from somewhere, and today we open the box that somewhere lives in, IAM. Before we go deep, let's pin down 5 terms that will anchor everything else. An IAM user is a long-term identity for one person or application, with a username, a password, and optional access keys. An IAM group is a collection of users sharing the same permissions. It's a management container, not an identity. An IAM role is an identity that trusted users or services assume to receive temporary credentials from a service called Amazon Web Services (STS). An IAM policy is a JSON document that grants or denies permissions, attached either to an identity or directly to a resource. And the principle of least privilege means granting only the minimum permissions an identity needs, expanding only when a specific task fails. Here's the uncomfortable truth about Amazon Web Services security. When you read the post-mortem on almost any cloud incident, the chain of events ends in the same place: a misconfigured identity, an over-permissive policy, a leaked access key. IAM is the foundation on which Amazon Web Services security stands or falls, which is exactly why understanding it deeply pays dividends across everything else in Amazon Web Services. Every single API call to Amazon Web Services, whether it's the console, the CLI, an SDK, or another Amazon Web Services service calling on your behalf, gets authenticated and authorized by IAM. There are no exceptions. IAM answers 2 scenarios for every request: who are you, and what are you allowed to do? It does that using 4 primitives: users, groups, roles, and policies. Everything else in Amazon Web Services security ultimately rests on top of those 4 pieces. Here are the 4 primitives we're going to take one at a time. Users are long-term identities for people. Groups bundle users who share the same permissions. Roles are identities for workloads, for an EC2 instance, a Lambda function, or a federated user. And policies are the JSON rules that decide who can do what. We'll start with users, but I want you to keep an eye on roles, because that's where the real story of this video lives. An IAM user represents one identity inside your Amazon Web Services account, ideally one person, or in some cases one application. Each user gets a username and a password for signing into the console. Optionally, you can give them access keys, which are 2 long strings, a key ID, and a secret, used for programmatic access from the CLI or an SDK. Here's the part that matters: those credentials are long-lived. They don't expire, and they don't rotate themselves. Whatever happens to them, happens to them. Think of an IAM user's access key as a house key on your key ring. It works as long as it's there, and the only way to make it stop working is to physically remove it from the keyring. If you drop that key in a parking lot, whoever picks it up can walk into your house until you change the lock. That's the mental model for a long-term credential. Because user credentials are long-lived, hygiene matters. Create 1 user per human, and never share a sign-in. Rotate access keys regularly, and delete keys that are no longer in use. And never, under any circumstances, paste access keys into your application code, into an AMI, or into EC2 user data. Automated bots continuously scan public Git repositories for Amazon Web Services key patterns, and practitioners report keys being weaponized by crypto miners within minutes of being committed. An IAM group bundles users who all need the same permissions. You attach the policies once to the group, and every member of the group inherits them automatically. When someone changes teams, you move them between groups instead of rewriting their policies. That's the whole purpose. A group is a management convenience for permissions at scale. It is not an identity, and it cannot do anything on its own. On the left, here's what groups can do. They contain users. They have identity-based policies attached. They deliver permissions at scale, and they get reassigned as people change teams. On the right is the part that trips people up in practice. Groups cannot contain other groups. There's no nesting. They cannot sign in or hold credentials of their own. They cannot be named as a principal in a policy. And in general, they cannot be used as an identity. Remember, groups have no credentials of their own and cannot appear as a principal anywhere in Amazon Web Services. They exist purely as an administrative container. The Amazon Web Services IAM User Guide settles any debate in a single sentence. User groups can't be nested. They can contain only users, not other user groups. There is no group hierarchy in IAM. If you need that shape, you flatten it, or you use multiple policy attachments. Quick check on where we are. Users are long-term identities. Groups bundle users so permissions stay manageable. But here's the thing, neither of these is the right way to give an EC2 instance permissions, or a Lambda function, or any Amazon Web Services service. For that we need the third primitive, and it's the spine of this video. A role is an identity that anyone, or anything, trusted by the role can assume. It's not tied to a single person. When something assumes a role, it receives temporary credentials from a service called Amazon Web Services (STS), the security token service. Notice what a role does not have. No password, no long-term access keys. The credentials expire automatically, and this is the right way to grant Amazon Web Services permissions to EC2 instances, Lambda functions, ECS tasks, and federated users from your corporate directory. If a user is a house key, a role is a hotel key card. You get it from the front desk. It works for the length of your stay, and at checkout it stops working on its own. If you drop a hotel key card in the parking lot, you didn't really lose anything. By the time someone finds it, it's already expired. That's the security advantage of temporary credentials. Here's what actually happens when an EC2 application reads from S3 the right way. You start with the EC2 instance running your application. You attach an instance profile to it, which is a wrapper around an IAM role. The role itself holds the permissions policy and a trust policy that says EC2 is allowed to assume it. Amazon Web Services (STS) then issues temporary credentials, and those get delivered back to the instance through the metadata service. Your code does nothing special. Boto3 or the Amazon Web Services CLI picks the credentials up automatically and rotates them behind the scenes. This is the single most important sentence in the entire video. If an Amazon Web Services service needs Amazon Web Services permissions, you attach a role to it, never an IAM user with access keys. Whenever an EC2 instance, a Lambda function, or any workload needs to call another Amazon Web Services service, use a role. Here's the comparison that defines this episode. On the left is the wrong way that engineers default to: create an IAM user, generate access keys, paste them into application config or EC2 user data. Now those keys stored in the AMI, in Git history, in shell history, and if they leak, the attacker has them until you rotate. On the right is the right way. Create a role with exactly the S3 actions needed, attach it through an instance profile, and let the SDK read rotating credentials from the metadata service. No long-term key ever touches the instance. Capital 1 shows what happens when you get one piece of this right and one piece wrong. An attacker used a server-side request forgery vulnerability on a misconfigured WAF to reach the EC2 instance metadata service. They stole the temporary credentials for that WAF's IAM role, and those credentials could list and read 106 million customer records from S3. Notice the lesson. Using a role was the right pattern. The policy attached to it was the failure. The WAF had S3 permissions far beyond what a WAF needs. Roles also solve a problem that comes up constantly in real engineering, giving people in one Amazon Web Services account access to resources in another. Account A creates a role and lists account B as a trusted principal in the role's trust policy. A user in account B then calls STS assume role and gets back temporary credentials. Those credentials are valid for, by default, 1 hour. So if something leaks, it expires on its own. And notice what never happens here. No long-term key ever crosses the account boundary. Now to policies, the actual rules Amazon Web Services evaluates. A policy is a JSON document with a handful of core elements: version, statement, effect, action, resource, and an optional condition. The effect is either allow or deny. You can attach a policy to an identity, a user, a group, or a role, or you can attach it directly to certain resources. Both are real, and understanding the difference matters in practice. Here's about as small as a useful policy gets. The version is a date Amazon Web Services uses to lock the policy language. The statement says, effect allow, action S3 get object, resource the reports bucket. Read it as one sentence. Whoever this is attached to is allowed to read any object in the reports bucket. That's it. That's the unit of permission in Amazon Web Services, and you'll see thousands of these in a real environment. Policies come in two flavors. An identity-based policy is attached to a user, a group, or a role, and it says this identity can do X. It travels with the identity. That's the most common kind you'll write. A resource-based policy is attached directly to a resource, and it says this principal can do X to me. The classic examples are S3 bucket policies, KMS key policies, SQSQ policies, and the trust policy on an IAM role. We'll dig into the cross-account implications in the next scene. Picture an office building. Your identity-based policy is the badge in your pocket, listing which rooms you're allowed to enter. The resource-based policy is the sign on the server room door, listing who is allowed in. You can get into the server room if your badge says you can, or if the sign on the door names you directly. Either side can grant access, and the door's owner controls the sign without touching anyone's badge. Quick check. Users and groups are identities for people. Roles are identities for workloads. Policies are the JSON rules attached to identities or to resources. The next question is the one engineers actually trip over. What does Amazon Web Services do when these rules conflict? That's policy evaluation. And there's one rule that resolves every conflict question you'll ever see. Here's the evaluation flow. Step 1. Every request starts in implicit deny. By default, you can do nothing. Step 2. Amazon Web Services looks across every applicable policy for an explicit allow. Step 3. It scans for an explicit deny anywhere in the chain. Step 4 is the rule that resolves every conflict. A deny overrides every allow, no exceptions. And step 5 is the decision. Allow only if there is an explicit allow and 0 denies. That single rule resolves every conflict you will ever encounter in IAM. The Amazon Web Services IAM User Guide states this as cleanly as possible. An explicit deny in any of these policies overrides the allow. Memorize that sentence. When allow and deny conflict anywhere in a request's policy chain, deny always wins. Picture the bouncer at a club with a clipboard. If your name is on the Do Not Let In list, it does not matter how many VIP passes you wave at him, you are not getting in. That's exactly how explicit deny works across every layer of IAM: identity policies, resource policies, service control policies, session policies, permissions boundaries. One deny anywhere ends the conversation. Now the identity that doesn't follow the normal rules, the root user. It's created with the account using the sign-up email and password, and it has unrestricted access to every resource. Here's the part that catches people off guard. You cannot attach an identity-based policy to root at all, and you cannot set a permissions boundary on it either. So nothing inside the account, attached to root, can reduce what root can do. That makes root by a wide margin the highest blast radius identity in Amazon Web Services. Treat it like the master key to a vault. The one way to constrain it is from above, using Amazon Web Services Organization's service control policies, or resource control policies, sometimes abbreviated RCPs, which can restrict what root is allowed to do across accounts in the organization. The hardening checklist for root is short and non-negotiable. Enable multi-factor authentication on the root user. Delete any access keys that exist for root. Programmatic use of the root user is just asking for trouble. Create a separate IAM admin user for your daily administrative work, and then sign in as root only when a specific task strictly requires it. Amazon Web Services' own guidance says, in plain language, don't use the root user for your everyday tasks. On the left is the pair worth locking together in memory. Close the Amazon Web Services account and restore IAM admin permissions if they ever get revoked. On the right are the other tasks that also require root. Change the root user's email or password, configure MFA delete on an S3 bucket, register as a seller in the reserved instance marketplace, and sign up for Amazon Web Services GovCloud in the US. The pattern is account-level operations that affect the existence of the account itself, or recovery actions that no other identity can perform. The principle that holds all of this together is least privilege. Grant only the minimum permissions an identity needs to do its job. Start with nothing and add permissions when a specific task fails, not the other way around. The path of least resistance is to paste administrator access on every role and promise yourself you'll tighten it later. That cleanup never happens. Least privilege is the design choice that limits the blast radius when, not if, a credential leaks. It's exactly the control Capital One didn't have. Amazon Web Services puts it about as simply as it can be put. Start with a minimum set of permissions, and grant additional permissions as necessary. That single sentence captures the entire design philosophy of IAM, and it's the correct answer to almost any question about how permissions should be scoped. 3 decision rules on the identity side. A human gets an IAM user, ideally managed through IAM Identity Center. A workload, EC2, Lambda, ECS, gets a role. Cross-account access also gets a role, and when many users share the same permissions, reach for a group. On the policy side, start with the default. Every request, before any policy fires, is implicit deny. From there, anything attached to a user, group, or role is identity-based. Anything attached to S3, KMS, or SQS is resource-based, and when allow and deny conflict, deny wins. 5 things to walk away with. The 4 primitives: users for people, groups to bundle users, roles for workloads, and policies as the rules. EC2, Lambda, and cross-account access always use a role, never a user with access keys. Groups contain only users, never other groups, and can never be a principal. Explicit deny always wins, and every request starts as an implicit deny. And finally, lock down root with multi-factor authentication, delete its access keys, and grant least privilege everywhere else. Now let's see how well that landed with a quick 5-question quiz. Alright, time to put your knowledge to the test. Question 1. A developer needs an application running on an EC2 instance to read objects from an S3 bucket. What is the most secure way to grant the required permissions? A. Create an IAM user with S3 permissions, generate access keys, and embed them in the application's configuration file. B. Create an IAM role with the required S3 permissions and attach it to the EC2 instance via an instance profile. C. Add the EC2 instance to an IAM group that has the S3 permissions attached. Or D. Use the root user's access keys on the EC2 instance and rotate them weekly. Pause here if you want more time. The right call here is B. An IAM role attached through an instance profile delivers temporary, automatically rotating credentials to the instance through the metadata service. No long-term key ever touches the instance or the code. A is the wrong pattern that most engineers default to, C is impossible because groups only contain users, and D is the worst answer in Amazon Web Services. Root should never be used programmatically. Question 2. An IAM user belongs to a group whose policy allows S3 delete object on a bucket. A bucket policy on that same bucket explicitly denies S3 delete object for that user. What happens when the user attempts to delete an object? A. The delete succeeds because the group's allow grants the permission. B. The delete succeeds because identity-based policies override resource-based policies. C. The delete fails because an explicit deny in any applicable policy overrides any allow. Or D. The delete fails because resource-based policies always take precedence over identity-based policies. Lock in your answer before I give it away. It has to be C, and here's why. Amazon Web Services evaluation logic is unambiguous. An explicit deny in any applicable policy overrides every allow, regardless of which policy type it lives in. D gets the right outcome for the wrong reason. The rule isn't that resource policies beat identity policies. The rule is that deny beats allow, period. Question 3. Which of the following tasks can only be performed by the Amazon Web Services account root user? A. Close the Amazon Web Services account. B. Create a new IAM user with administrator permissions. C. Attach an IAM policy to an existing role. Or D. Launch an EC2 instance in a new region. Pause here if you want more time. The right call here is A. Closing the Amazon Web Services account lives on Amazon Web Services' official list of tasks that require root credentials. No IAM identity, no matter how privileged, can do it. B, C, and D are everyday operations that any sufficiently permissioned IAM identity can perform. Question 4. A company wants to organize its IAM permissions for 200 developers across 3 engineering departments. Which approach reflects how IAM groups actually work? A. Create a top-level engineering group containing 3 department-level groups, each containing the relevant users. B. Attach policies directly to a group, then list that group as the principal in resource-based policies on shared S3 buckets. C. Create a single group containing all 200 users and rely on conditions in the policy to differentiate departments. Or D. Create one group per department, attach the appropriate policies to each group, and add each developer to their matching group. Run the decision rule from earlier before you answer. If you said D, well done. One flat group per department, with the right policies attached, and each developer placed in their matching group. That's how IAM groups actually work. A is impossible because groups cannot be nested. B is impossible because a group is not an identity and can never be a principal. C technically works but defeats the entire purpose of having groups in the first place. And a quick note worth memorizing: an IAM user can belong to up to 10 groups, so a developer who works across departments could be added to more than one. The cap is 10. And the flat per department structure is still the right pattern. Question 5, and this one's a callback. Let's test a concept from an earlier episode. Under the Amazon Web Services shared responsibility model, which of the following is always the customer's responsibility, regardless of which Amazon Web Services service they use? A. Patching the host operating system that runs underneath the hypervisor. B. Securing the physical data center facilities and hardware. C. managing IAM users, roles, and the policies attached to them. Or D, maintaining the global network fabric that connects Amazon Web Services regions. Got your pick? Let's see. This one is C. IAM configuration is always part of security in the cloud, and it never shifts to Amazon Web Services, not for EC2, not for RDS, not for Lambda, not for S3. A, B, and D are all examples of security of the cloud, which Amazon Web Services handles for you across every service. That's why IAM mistakes are always the customer's problem to fix. That's IAM fundamentals, users, groups, roles, and policies, demystified. If you got value, the subscribe button is the best thank you there is. Next lesson is already cooking.